Well, we're live and on camera, and we're in chapter 5. Yes, we're in chapter 5, the last half of the chapter. And so we're going to go with Euler theorems. This is where we're going to learn how we can make things easier for ourselves. And then we get more difficult, and isn't that lovely? So we're going to develop some things to determine whether or not a graph can have an Euler circuit or an Euler path, or neither. And so if a graph is connected and every vertex is even, then it has an Euler circuit. At least one, usually more. If a graph has any odd vertices at all, then it cannot, does not, will not have an Euler circuit. So all the vertices have to be even. If any of them are odd, then no, I can't have an Euler circuit. Here's how an Euler circuit theorem works. First, we make sure the graph is connected. Then we count and see whether or not we have even degrees on all our vertices one at a time. And then we say whether or not we do or don't. So here's a guy. 2, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4. So that has an Euler circuit, at least one. We're connected, we're even. That guy's got an Euler circuit, at least one. I can find this one very easily. So I've got 1, I've got 2, I got 3, I got 4 on that guy. This graph is connected, but at vertex C, I've got 1, 2, 3. I'm odd. I have a odd at C, I'm odd at G, I'm odd at E, and I only have to be odd at one of them, so I have no Euler circuits. I don't even have to look. I cannot have them. I look at this guy, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 1, 2, 1, 2, 3, 4. I do have an Euler circuit. All of the, I'm connected, all the vertices are even. Therefore, there is at least one Euler circuit, probably many. Every time you go through a vertex, you use 2 different edges, one to get in and one to get out. That's why we have to be even, and if we're odd, then we can't do that. That's the whole thing. Euler path. If a graph is connected has exactly 2 odd vertices, then it has an Euler path. We start at one odd vertices and we end at the other odd vertices. If the graph has more than 2 odd vertices, it cannot have an Euler path. So with exactly 2, I can have an Euler path. With more than 2, no Euler path. So now we come back to our cones and bridges problem, and we look at it. We're connected. I got 1, 2, 3. I've got 1, 2, 3. I got 1, 2, 3. I got 1, 2, 3, 4, 5. I have too many odd vertices. So I have a odd vertices. I can't have an Euler circuit, and I have more than 2 odd vertices. Therefore, I have no Euler path. What a pity. So now we have an unequivocal answer to our problem of bridges. And we see that if we added another one, however, right there, then everything would be fine. And we could actually do it. So all we have to do is add one lousy more bridge. Okay, so now we're back. We have something that's connected. And the issue is, do we have an Euler circuit? Even. Everybody's even. Therefore, there is an Euler circuit, at least one, probably more than one. Do we have an Euler path? No, because we have to have odd guys. We come back to this guy. I am even, odd. I have Euler paths, but no Euler circuits. I can't start an Euler path at A, B, or E, but I can start an Euler path at D or C. That'd be perfectly okay. I have 4 odd vertices. I do. 1, 2, 3, 4, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yes, I do. A, B, C, and D are all odd. No Euler circuit, no Euler path. Done with the problem. Moving on. Yeah. Well, we're connected. I can tell that. 1, 2. Let's see. We'll start. Where's A? 1, 2, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 1, 2, 3, 4, 5, 6. G, H, 1, 2, H, I, 1, 2, 3, 4, 5. I have an odd guy at I, and I bet you I've got an odd guy at K. 1, 2, 3, 4, 5 at K as well. So I and K are odd. 1, 2, 3, 4, even, even, even. 1, 2, 3, 4, even. 1, 2, 3, 4, even. So no Euler circuit. I'm odd, but I have an Euler path either starting at K or at I. If I start at K, I got to go to the left because I have to end up coming into I. So that wasn't that bad, I don't think. On the other hand, we can quickly check are odd and all the rest are even. Okay, so that we already did that. Third Euler theorem deals with a graph with 0 odd vertices, whereas Euler's path deals with a graph with 2 or more odd vertices. The only scenario not covered by the 2 theorem is that of a graph with just 1 odd vertices. Now, what if I just have 1 odd vertex? The sum of the degrees of all the vertices of a graph equals twice the number of edges, and therefore it is an even number. The graph always has an even number of odd vertices. The sum of the degrees of all the vertices of a graph equals twice the number of edges. Okay, well, that's okay, that's fine. And a graph always has an even number. Okay, that's fine. Euler's sum of degree theorem is based on the following. Okay, well, I think that's perfectly okay. Since the total sum of the even numbers is impossible, it's just 1 odd vertice or 3 odd vertices or 5 odd vertices and so on. To put it in a slightly different way, the odd vertices of a graph always comes in 2s. All right. So number of odd vertices. 0 odd vertices, we have an Euler circuit. 2 odd vertices, we have an Euler path. 4, 5, and 4, 6, or 8, we have neither. 1, 2, and 3, we have to go back and double check. It's impossible. So I can't have 1 odd vertex, right? Because how would I have 1 odd one? I'd have 2 odd ones, right? So if I count and I have 5 odd vertices, then I know I'm hosed. Okay. We'll proceed to see if we can do a problem. And the next problem is 27. And in 27, we're supposed to 1, does it have an Euler circuit? 2, an Euler path. 3, neither. Okay, so that seems like a reasonable thing to do. So we're looking at problem number 27A. And I'm not going to redraw it. I'm just going to look and count. Even, 1, 2, 3, 4, odd. 1, 2, 3, 4, odd. 1, 2, 3, 4, even, even. 1, 2, 3, 4, even. 1, 2, even. 1, 2, 3. I have 2 odd guys. I have 2 odds. So if I have 2 odds, so I have no Euler circuit. Okay, so I know it, but it has an Euler path. So that means I have an Euler. We stopped because of the 10-minute problem. Graph B. I'm going to look again in 1, 2, 3, 4, 1, 2, 3, 4. I'm now even everywhere, and because I'm even everywhere, I have an Euler circuit. The graph with 6 vertices, all of 1 degree. Okay, so I'm going to have 6 vertices, all of degree 1. Does that graph meet the requirement? It's a graph with 6 vertices, all of degree 1, right? Okay. Let's see. Clearly, it can't have an Euler path. It can't have an Euler circuit. The graph neither has an Euler circuit or path. There's no may or may not about it. The graph may or may not. There's no may or may not about it. So that'd be a triple I. Unless you want to come up with something, a different graph. Okay. Yeah. There we go. That's different. Okay. Well, that was a total waste of time there. Number 31. 31. We have to find the path. Jack set out to find an Euler circuit for the graph below. He started at the labels. He started at 1, and so on. And our job is to finish. Okay, so I got 1, 2, 3. All right. So yeah, I think that's particularly obvious, right? What we're going to do here. If I can draw it in the first place, then I can say so. The first part goes. Well, I guess we have to draw in these guys too, don't we? Alright, so assuming that I got the picture right, I'm going to start there, and I'm going to go like that. And now I've got to finish it off, so I'm going to go, how do I get back to the middle? Oh, I don't have to get back to the middle, or do I have to get back to the middle?
On the circuit.
I don't know. If I do, I was thinking I'm doing this. Is that what you're thinking?
Yeah.
But if I do that, I didn't take those paths. Aren't I? I'm supposed to take those paths, aren't I?
Well, then you just go down, over, up, over, and then back.
Oh, yeah. I see my problem. My problem is that my trifocals got in the way, and I didn't go this way.
Yeah, you gotta go down.
Yeah, I didn't go that way. All right, and now I'm right here. So I'm right there, taking off, and now I'm going to do this. And now I made it. Okay, good enough. Maybe we should add some arrows going that way, that way, that way. All right, well, that's 31. I'm not sure I want to do 35 yet. Maybe I do. 35. Find an Euler circuit for the graph. Use B as a starting point and the end point of the circuit, and label edges 1, 2, 3, and so on in order as you travel. Now, I don't think I want to do that yet. I want to go back to my transparencies for a moment. So we'll open the next transparency and hope it gives us a plan to do it. All right, so this is well, how do you pronounce that, I wonder? Fleurier? That sounds too French. It's got to be more German. Fleurier. I don't know. That's why I'm a math guy and not an English guy. When Euler's passing theorems to find small graphs, blah, blah, okay? Now we have a way to do it, and this is what we're going to do. There are different types of problems that can be solved different ways. After you finish this, so what you do, you follow these rules. Given a specific starting point, you follow by a set of procedures, blah, 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 until you're done. Directions, you find somebody's house, blah, blah, okay. So here we go. We will now turn our attention to an algorithm that finds an Euler circuit or an Euler path in a connected graph. All right, so that's what we're trying to do. And we're not going to burn bridges. Okay. So because, see, if I walk across the bridge and I'm not done on this side, then it's not going to work. All right. It's based on the simple principle. Find an Euler circuit or a path. Bridges are the last edges you want to cross. Our concern lies only that we get around before we go across the bridge. Okay, so make sure that the graph is connected and it has no odd vertices for a circuit, just 2 odd vertices for a path. Choose a starting point. This can be any vertex, or it must be one of the 2 odd ones if we're going on a path. At each step, if you have a choice, don't choose a bridge unless you're done. When you can't travel anymore, it's completed. All right. Now, bookkeeping, what are we going to do? We're going to keep track of where we go by numbering things and erasing them when we get done. Each time you travel along an edge, you erase the edge from the copy, make a mark that says that it's done, etc. Okay, so we start with something like this, and we start at F, so there I am starting at F. I move down to C, and then I move over to D, and as I do that, I'm erasing things. So it may not have been clear, but now that I'm at A, it's very clear I want to go that way. And because I don't want to go that way because that'd be a bridge and that would be unsat. So as I walk around the circuit, I end up erasing things as I go. Okay, so now we're going to apply this to the graph below. So I'm going to make sure that everything is even. And yes, it's all even, so that's good. And we're going to start at some place, and wouldn't it be nice if they did it? Okay, so they started at some place, they moved around. We have something that looked like that now, and where are we? Choose G. Okay, if we choose to go across that way, then we're hosed. We're not going to do that. But we started at J, and that's what we're going to do. Now we're going to do probably something like that. We're not going to go across G. And there we are, we're all done. Isn't that pretty? I would have done it in multiple colors myself, but that's all right. Prettiness is good too. Now we're ready to do problem number, whatever it was, 35. Now we're ready to do 35. But in order to do 35, we have to draw things smaller than I really want to. All right, so 1, 2, 3, 4, 5 across. 1, 2, 3, 4, 5 down. Okay. Now 2 here, 2 there. Okay, I think that's right. Now the glory of the smartboard should we label these guys? Probably not. A, B, C, D, E, F, G, H, I, J, K, L, M. Alright, so use B as the starting point. Alright. Now, because I'm using smartboard technology, I can just copy this and it'll never go away. So just copy, and now I can just paste it. That wasn't brilliant. Okay. So we're going to start at B. And that's my eraser. So I'm going to go 1, 2, 3, 1, 2, 3, 4, 5, 6, 4, 5, 6, and we'll change colors. 7, 8, 7, 8, 9, 10, 11, 12, now do I want to go this way or that way? Or doesn't it matter? It probably doesn't matter. 12, 13, 14, 15, 16, 17, 18, 19, 20. Oh, I think I'll go down. 21, 22, 23, 24. 25, 26, 27, 28. What am I doing? I'm making a circuit, so I have to get back to there. Okay, so that's what I want to do. I think I'm hosed. What do you think? Oh, maybe not.
No.
Okay, I do this, see this guy's odd now. I gotta get back to B. Find an Euler circuit. Use B as the starting point. B is the ending point. Okay. Alright. If I think I'm okay.
Cross down over
1, 2, 3, 4, 29, 30, 31, 32, 33, 34, 35, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, right?
Yep.
Can I do that again? Did I go up first?
Now you want to cross.
I want to crossway. How come I got two 35s?
The bottom one's supposed to be 34.
34, 35. So I'm here. So I'm going to go, I'm here. I'm going to go that way, this way, this way, this way, this way.
Oh,
No?
you deleted that one.
I'm here right now, right?
Oh, you're there, okay.
I think I'm there. So I'm going to go boom, 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 boom. I can't do that. I'm going to go boom, 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 boom. I had it. Now I don't have it anymore.
You want to go
That way.
over, down, over, up, over, up, over. It's there. Yeah, the down, over, up, over, down, over, up, over.
Okay. We got it?
Yep.
Okay. Check. Must be right. Okay.
You want us to write our
Well, once you get that far, then that's what you do from there on. Is that messy enough?
yeah.
So what I would do is I would do every 10 and redraw.
Every 10 or
Yeah, that's well, that might every 10 and redraw, that might be an okay thing to do. And maybe that's what I should have done too. I should have copied it and moved it before I did the next ones. All right, well, we'll do it over.
Okay.
Okay, because I can paste it in there again, and then we can start over at B. So we're gonna go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. And we'll just copy that. Paste that. Okay. Then we can, so we're here. 8, 9, 10, 11, 12. 8, 9, 10, 11, 12. Copy.
How do we have 40?
5 by 5, 25, but twice that number of edges plus the double edges, so it's 56, 51, 52, 54, 55, 56, 57, yeah, around there, less than 60. Okay, so we're at 12, 13, 14, 15, 16, 17, 18, 19, 20. So we're at 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so we're at 20, which is right there. I think I'm going to go down. 21, 22, 23, 24, 25, 26. 21, 22, 23, 24, 25, 26. Okay. 37, 38, 39, 40, 41, 42. 37, no, 37, no. Okay, 26 got me there. Okay, 27, 28, 38, 39, 40.
I think you're still in the 20s,
Okay,
or in the 30s.
okay, so I'm at 26.
27.
I'm going to go up for 20. No, I'm going to come over. So I got 27,
28.
28. Then I'm going to go up for 29. Then we're going to come up here for 30, 31, 32. All right. Didn't confuse myself too awfully much. Yeah, cut. That's just what I want to do. Cut. Okay, so I'm at 32.
Down over.
Okay, so that's what I just did will work. All right, so I'm going to go 33, 34, 35, 36, 37, 38. 33, 34, 35, 36, 37, 38. 39, 40, 41. 39, 40, 41. 42, 43,
No.
44.
Oh, yep.
Yeah, I'm good. 42, 43, 44, 45, 46, 47, 48, and I'm back where I started from. 44, 45, 46, 47, 48. Okay. If that wasn't a POS, I don't know what is. It's pretty bad. And there's one last section, but we have no problems to work, so this is probably Euler rising graphs. Oh, so this is what we do is we have a graph that isn't right. We're going to add something to it to make it right. All right, so there's common thread needs to have an optimal root for the exhaustive root passing through many things, and maximizing. Eulerizing, we're going to add duplicate edges in strategic places to make it work. Okay, so here we've got 1, 2, 3, 1, 2, 3, 1, 2, 3. We have all these places with 3 vertices. Obviously it's not going to work, so I add more paths, so now I'm even everywhere. Now I've Eulerized it, and now I can make it work. Alright, so, and there's a thing telling me that I made it work. Okay, isn't that lovely? Now I have the same way. I've got more odd. I need to Eulerize it. I'm going to go across. I'm going to come over. I'm going to make it so that it'll work. And all right. Excellent. And got to do the same way again. Excellent. All right, enough of that. On to chapter, what are we doing next? Chapter 8?
6.
6? We're doing chapter 6 next?
Yep. We don't even have 8, 6 and 1.
Bummer. All right. So I hope chapter 6 is better than chapter. Well, it's going to be better. They're going to get better as we go on, because someday we're going to get to money, and we're all going to love money.
Perhaps.
Maybe. All right. So in chapter 6. Now we have Hamilton paths, Hamilton circuits, complete graphs. Oh, I like that, 6.5, brute force. Isn't that good? That's obviously where we can't possibly do it. And the cheapest link, I like that too. That's all right. All right, so in chapter 5 we had Euler paths, Euler circuits. And because we're taking every edge. Now we're going to have Hamilton paths, Hamilton circuits, and where we're going to just go through every vertex. So we don't have to use every edge, but we have to include every vertex. A Hamilton path is a path that includes each vertex once and only once. A Hamilton circuit includes each vertex of the graph once and only once, but ends up in the same spot. Okay. So I got something like this. And now I can have a Hamilton path. Boom, I went through everything only once.
That's path.
Yeah, that'd be a circuit.
Oh, sorry.
Yeah, but if I had this, then I could have a Hamilton path.
Oh.
Go through everyone only once.
Oh. And circuit goes back to the start.
Yeah, circuit will go back to the starting point.
Gotcha.
All right. The Euler guy has to do it, but the other guy has to go everything. So here I got 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3 there. Now the Euler guy would have to travel every path in order to have an Euler circuit, but the Hamilton guy can do it with only traveling, doesn't have to take every edge. He just has to go through every vertex.
Yep.
All right. Maybe I'll remember that long enough to solve problems, who knows. And the circuit returns the same vertex, the starting one doesn't. On the surface, there's one word different, and that is vertices, all vertices covered instead of all edges covered. But that probably makes a lot of difference, and I probably skipped 2, so I better go back 1. Yeah. So I show a graph, even, 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 even. Everything's even. I have a Euler circuit can be there, and it also has a Hamilton circuit. One of the guys, A, B, C, D, E, G, blah, 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 blah. There are plenty more, but there's more of them. So I can make a circuit like that. I can make one like, no, I can't. But anyway, there's more than one. If the graph has a Hamilton circuit, then it automatically has a Hamilton path because I just truncated off at one spot. So if I have a Hamilton circuit that goes A to A, I can have a path going A to E, just get rid of the last guy. So here's something that I can't have an Euler thingy on, because I can have an Euler path because I have 2 odd guys, but can't have an Euler circuit. But I can clearly have a Hamilton path going that way. Can I have a Hamilton circuit? No, I can't have a Hamilton circuit either, because but this guy can have probably both. There's plenty of different Hamilton guys. Alright, sounds like fun. I'm sitting out here. I can't have a circuit because I'm truncated, but I could have. I can't have a Hamilton path either, can I? Well, I can have a Hamilton path, but I can't go through everything. The figure shows no Euler circuit, but it has an Euler path, and it neither has Hamilton circuits or paths because I have to go through everything. I can't get there from here. And I still don't have a Hamilton circuit because I still can't get back. Yeah. So here we have a summary of things. Yes, no, in between, no, yes, yes, no. All right. Obviously, that'll be a good quiz question, right?
Yeah.
Bunch of random things and disconnected stuff. And the lesson is that the existence of an Euler path or circuit tells us nothing about the existence of a Hamilton path or circuit. Isn't that great? There's no theorem exists that determine whether or not a graph will give you a Hamilton circuit or not. Isn't that lovely? Oh. Open section 2. Complete graphs, also known as K-graphs. Sometimes a Hamilton graph, obviously. A complete graph means that every single vertex goes to every other vertex. What kind of garbage is that anyway? So that'd be a complete graph. That'd be a complete graph.
So long as
they're all connected. I'm not sure whether or not we have to go that way. But if I have 4 of them, then he's got to go to each of them, and he's got to go to each of them, and he's got to go to each of them. So this guy is hooked up to all 3. He's hooked up to all 3. He's hooked up to all 3. He's hooked up to all 3. So that'd be complete. If I have 4, if I have 5, so I can do it with 5. This guy has to be hooked up to the other 4, and then this guy has to be hooked up to the other 3, and then that guy's got to be hooked up to the other 2, and that guy's going to be hooked up to the other 1. Boom. All right, so we have 1 there. We have 3 here. 1, 2, 3, 4, 5, 6. We have 6 there, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Do we have 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 there. There's got to be some math associated with that. Get to the next slide. We'll see whether or not it tells us. Next slide, please. There we go. Oh, there we go. The key, so we're going to have Kn is, where n is the number of vertices. The degree is of every vertex is n minus 1, which means we have n minus 1 factorial divided by 2 to be the number of edges. So n times n minus 1 divided by 2 is the number of edges of our graph. N times n minus 1 divided by 2. So we'll go back to here. 2 times 2 minus 1 divided by 2 is 1. So I have 1 edge. Excellent. 3 times 3 minus 1 divided by 2 is 3. So I have 3 edges. 4 times 4 minus 1 divided by 2 is 6. So I have 6 edges. 5 times 5 minus 1 divided by 2 is equal to 10. So I have 10 edges. So this is K2, K3, K4, K5. So if I have K137, I have 137 vertices, all of them hooked up to each other. So 137 times 137 minus 1 divided by 2 gives me the number of edges that I have. And wouldn't it be better if I wrote it so it looked like it was math and not some scribbly stupid thing like that? Is equal, okay, so where's my calculator? 137 times 136 divided by 2. I've got 9,316 edges. Now, if I have, let's say that I've got 100 PCs on my network. How are those PCs connected to each other? Each of those PCs are at a vertex, a node, right? Can each of them talk to each other on that network? Yes, they can. So those are the number of communication channels I have on that network. Would be, I'd have a perfect graph. K100, 100 times 99 divided by 2. 100 times 99 divided by 2. 4,950 possible communication paths on my network, all trying to communicate at the same time. If we travel the 4 vertices of a K graph in an arbitrary order, we get a Hamilton path. So I just follow them in some random order. Where am I starting anyway? C, boom, 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 boom. I get a Hamilton path. Each of these Hamilton paths can be closed back on each other, and then I can have a Hamilton circuit. So I can have a Hamilton circuit from any point, whatever point I start at, as long as I have a K graph, a complete graph, everything hooked up to everything else, I can always have a Hamilton circuit getting back to where I'm starting, and I can always have a Hamilton path by truncating one of them. Isn't that nice? So here's our, we have a K4, and we have a starting point A, and from that starting point I got 1, 2, 3, 4, 5, 6 possibilities of Hamilton circuits, and from B I can do the same thing. I have 6 possibilities, C 6, D 6, and clearly we're going to get stuck with writing all those down some other time, right? Hopefully we get for a K3 or something in the homework. Try to list all the circuits for K5. Well, from any particular one I'm going to have 24. So 24 times 5, there'll be 100 and some of them. Well, that's going to be a pain in the rear end to try to do. So let's hope we don't have to do that. So from any one point, I would have 24 of them. So there's 24 starting at A. And then there'd be 24 starting at B, 24 starting at C, 20, etc. All right. There's 3 of them. Well, that's just what we wanted to know. The number of Hamilton circuits, okay, was going to be n minus 1 factorial. Now, do you each have a calculator with a factorial key on it?
Sure.
Yeah, so if you do, then that's okay. So the number of Hamilton circuits, n minus 1 factorial. So the number of edges, n times n minus 1 divided by 2. N vertices, no multiple loops, no whatever. K16, 1.3 trillion Hamilton things. K32, 8 trillion, 8 billion trillion. 8 billion trillion trillion. Oh, gee, calculator doesn't do that. So that'd be 31 factorial. Well, I think my calculator does 31. I think it gets up to, yeah, I mean, 31 factorial. Yeah, 8.2 times 10 to the 33. Got plenty of room on my calculator to do 31 factorial. All right, so there we go. I'm doing n minus 1 factorial, and I'm done with, is that 3? That's 2. And maybe we should look at homework problems, yeah. So we don't get, otherwise we'll get confused by the facts. Yeah, we don't want to get too many facts. We just want to, okay, so I'm in chapter 6, looking at problem number 1. Okay, excellent. I'm looking at A. Find 3 different Hamilton circuits. All right, so I got this guy over here. 1, 2, 3. One guy there. 1, 2, 3. Okay, we're connected across that way, down that way, over there, up there. Across like that. Down like that. Over there, over there, over there. Down, down. Okay, so do I have it? I think I have it drawn right. Okay. So we'll do we need 3 of them. So we'll do a copy, and we'll paste this guy. 1, 2, 3. Excellent. Okay, so if I start at A, I want to end at A. Boom, boom. Boy, am I hosed. No, yeah, I can't do that. Can't do that. Boom. All right, so I'm going to have to go dom, 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 No, can't do that either. That is one. 1, 2, 3, 4, 5. There's one. Okay, so I got one. All right, now I'm going to do it again. Should I start at A again? All right, I'm going to start at A again. 1, 2, 3, 4, 5, 6. Boom. Okay, so there's 2. Are those guys different? Yeah, those are different. All right, so we'll go in View, Zoom, 50%. Now can you tell that they're different? One I come up that way, and the other one I don't.
You want us to write it down or just write the word in the letters?
Well, you could write it down, yeah. You could do that. You could say, if we had the letters written down, A, B, C, D, E, F, oh, that's G, G, F, E. So the first one is A, G, F, E, C, D, B, A. So that'd be the first one. And the second one is A, G, F, C, E, B, D, A. Okay, now we need a third one. Now what color? We'll use this color. All right, so we'll start at A, and we'll come down that way. 1, 2, 3, 4. Then unhosed.
You go over it, up, down, back.
Yeah, can't do that though.
Yeah.
Okay, so I'm going to start here. You want me to come down? Okay, so I'm going to come down. 1, 2, 3, 4, 5, 6, 7. How's that? That work?
Yep.
And is that a different one? Yes, it is. Okay, so I'm going to do A, F, E, A, F, E, C, D, B, G, A, G, A. Okay, so I've done 3 different Hamilton graphs. Find a Hamilton path that starts at A and ends at B. Okay. And so edit, paste. Move this guy down a little. Well, that's stupid. All right, now I got it all. Okay. So now I'm doing the B part. I want to start at A, end at B. And we'll do it in red. Okay. 1, 2, 3, 4, 5. Oh, that's all right. Boom, 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 boom. Boom, boom. All right, now. Boom, 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 boom. Okay, so I went A, G, F, E, C, D, B. Find a Hamilton path that starts D, ends F. You know, I go C. Okay, so I want to start D, end F. File, paste. Okay, so where's D? Starts D, ends F. Okay, so boom, boom, no, boom, no, boom, 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 boom. Boom, boom, boom. That's not what I did. Boom, boom, boom.
Now go EAG. So you want to go over and then go down.
But if I go down, oh, right.
And go up to B.
Yeah, I know, yeah. All right. Boom, 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 boom. All right, so I'm going D, A, G, B, C, E, F. Okay, so I'm done with problem number 1. Excellent. We'll look at 15. 15. Find a Hamilton path that starts A and ends at B and give its weight. Well, obviously we can't give a weight yet because we haven't gotten that far. Okay, so we can't do that one yet. Okay, so that's fine. And we've done section 1 and section 2. So now we're going to do section. Well, are we done with section 2?
I thought so.
I thought we were too. Yeah. Yeah, we're done with section 2. All right.
3.
So now we'll open section 3. All right, traveling salesman problem. All right. Traveling salesman has an edge to go on, but he also has a distance to go on the edge. And we want to find, so each of these paths that he's on is going to cost him something. He's flying. Where are we going to fly for $100 anyway? $150. I mean, this is pretty silly. But he's these distances that he can fly, and he's trying to find the cheapest route to go from A. And so then here we are. We're going to go around the moons of. We're going to go from the Earth to out to the moons that are around Jupiter. Are those guys all around Jupiter? Titan's around Jupiter. But Minos and Cassio, I think those two are around Mars. Ganymede, Io, I think might be Saturn, might be. Anyway, it doesn't matter. So we have these moons we're going to tour, and we're going to have to figure out what the shortest distance is. I have a rover on Mars, and I have a graph of how far is it from A to G and A to F and A to I, and now I have a distance thing without having any lines. All right, well that's good. So now we're going to go and find some optimal thing, and none of that looks all that important. All right. So we have sites, we have costs, which are on the edges. We have a tour, which is a Hamilton, and the optimal tour is the one that costs the least. Okay, now we're ready to go.
That was quick.
Yeah, we didn't want to waste that. You didn't want to waste that much time there, right? I mean,
No.
no, I didn't think so. View, zoom, and besides, you can always read the book if you have to, right?
Oh, yeah.
I mean, really. Bought the book anyway. 15. Weighted graph 64. Okay, so I see it over there. So there's my graph. I got a circle thingy, and I got a triangle thingy, if I could draw a triangle thingy. Triangle thingy. And I got points there, there, here, and here. And I got 10, 12, 11, 4, 5, 6, 2, 3, 7. And I got an A, a B, a C, a D, an E, and an F. All right, so I get a 4-0 for drawing the picture. And now I want to find a path that's any path. Starts at A, ends at C. Okay, but before we do that, we're going to make a copy of this so that we don't destroy the original, so I don't have to do it again. Try doing that on a test sometime. Making a copy first. It works so much better. Paste. All right, so here we go. A. Okay, we want to start at A, end at C. All right, so I'm going to go boom, boom, boom. That doesn't work. Boom, 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 boom. That works, right? I'm going to start here. Do, dum, 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 dum. Okay, so my path is A, D, F, E, B, C. My weights are 2, 7, 5, 4, 11. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 29? All right, so now I have a Hamilton path with a weight of 29. Problem A solved. B. Find a second one. Okay, so I want a different path than I had before. And of course, if I obscure the path I had, then you won't know whether or not I'm using the same one or not. So that'll be good. All right, so last time I did this. This time I'm going to do A, B. Oh yeah, I see it. Okay, so this time I'm going to go 1. No, I'm going to go there. And I'm going to go like this, and then like that. Okay, so I'm going A, B, E, D, F, C. So I got a different path, and my weights are 10, 4, 3, 7, 6. 30. All right. Find the optimal path that starts at A and ends at C. Well, clue 30 is not the optimal one because 29 is better. So now the issue is, can I get better than 29? That's the issue, C. Can I even paste my drawing again? That's the other issue. Close myself over bad there, didn't I? All right, so if I would like to take the 2. I've already done that. 10. Already did that. I think I already have it. 2. Yeah, 2, 7, 5. I already have it. So the 29 of A is the optimal one. Optimal. So we by mistake got it already. Because I don't see one any better than that. I have a choice. I either go A to B or A to D. once I get to D, the only way I can go is to F. Because if I go to E first, then I'm stuck. I can't go the other way. Okay, so that's good. Got that one done. 17 is next. Oh, well, we're going to do 17. That's just a bunch of factorials. All right, so given that 10 factorial is 3, 6, 2, 8, 8, 0, 0. What is 9 factorial? Well, 9 factorial would be just that divided by 10, so we just take off a 0. 2, 8, 8, 0. And then if we go and put 9 factorial in our calculator, it should probably tell us that. 3, 6, 2, 8, 8, 0. So it tells us that. So that's good. I'm glad I did that. A, B. If I have 10, 11. 11 factorial divided by 10 factorial is going to be 11. And then C, 11 factorial divided by 9 factorial is going to be 11 times 10, which is 110. And 9 factorial divided by 6 factorial is going to be 9 times 8 times 7. Oh, which I don't know. 9 times 8 times. I should know those numbers, right? 504. 504. And I could have put in my calculator, I could have gone 9 factorial and divided by 5 factorial, right? I could go 9 factorial divided by 5 factorial, and I would have gotten a different answer. 9 factorial divided by 6. If I divided by 6 factorial, I'd still get the same answer. Okay, so that's good. E. Now this is one where you could hose yourself over. 99 factorial, because if you put 101 factorial into your calculator, it'll probably give you an error. So you couldn't just put 101 factorial divided by 99 factorial. That's clearly 101 times 100, which would be 10100. So you'd have to get the answer that way. 17. Well, let's hope we have some factorial stuff on the next test. 27. Okay. Yeah, we can do 27. 27. We have Kn, and it has 120 Hamilton Dewey Dobbs. What is K? Well, this guy's got n minus 1 factorial Hamilton thingies. So n minus 1 factorial has to be 120, which is obviously 5 factorial, which implies n has to be equal to 6. So this is going to be K6. I guess I had to think too much on that one. Did I have to think too much? That's A. B. Okay, Kn, and I have 45 edges. Okay, so n times n minus 1 divided by 2 is 45. So n times n minus 1 is equal to 90. So what the heck is that? N squared minus n minus 90 is 0, and we can factor it. That looks like too much work. Okay, some number times some number 1 less. I'm going to go 10 times 9 is 90, and is equal to 10. K10. Now I could have gone the other way. I could have said n squared minus n minus 90 is 0. And then I could have said quadratic formula, right? So n is equal to 1 plus or minus the square root of 1 minus 4 times 90 minus 90 divided by 2, right? I could do something like that. And then, so 90 times 4 AC, right? Okay, 90 times, what's this what a garbage here. Okay, so 4 times 90 plus 1 equals 361. The square root of the answer, way to go, error already. The square root of the answer, 19. Alright, so that's going to be 1 plus or minus 19 over 2. So that means n can be 10. Duh, hey, I used math. Now, we're going to go over something else. You're not going to like it. But if I have a squared, if I have a x squared plus b x plus c is equal to 0, then, okay, that's all right. I can use a quadratic formula, right, and say x is minus b plus or minus square root of b squared minus 4ac divided by 2, right?
I remember that.
Okay. Now, this is what the math people hide from you. If I have ax squared plus 2bx plus c is equal to 0. So that means this is an even number, 2b. Then x is going to be minus b plus or minus the square root of b squared minus ac divided by a. Now, if you think about it and you say, well, if I put 2b in here, then I got minus 2b. If I put 2b here, then I have 4b squared there. I can bring the 4 out. I don't have if I had a 2 here, I divide it into those guys. But this guy here, if you look at that calculation and how you get it, and then you look down here and see that this is a whole lot easier. If I just divide my even number by 2 and use a different b, this is called the half quadratic formula, and I get the answer sooner, if I'm interested in the answer sooner. Okay, C. Is there a D on the other page? No, good. Oh. Okay, good. So C, we have Kn, where I have 20,100 edges. Okay, so n times n minus 1 divided by 2 is 20,100. N times n minus 1 is 40,200. So now the issue is, what is n? Well, if I go 40,000, I go the square root of, I take the square root of 40,200, I get 200.5. So I bet you if I take 201 times 200, I get that number. And sure enough, I do. Check. So this is K201. 27. 29. Well, brute force, nearest neighbor, blah, blah, blah. We not that far yet. Okay. Section 4. Open section 4. Simple strategies for solving traveling salesman problems. All right, simple strategies. All right. So first of all, we would pick the first guy we'd pick would be the cheapest guy. So we find this guy and we say, well, if I pick the cheapest one first, and then the cheapest one left over next, and the cheapest one left over after that, and the cheapest one left over after that, then that might solve the problem. So you may want to have somebody. So we could have an exhaustive search and look every single solitary path. If we did that, that might take us the rest of our natural life, depending on how many paths we have. Or we could go cheap and just use something else. So this is a possible strategy. Make a list of all possible Hamilton circuits, find the weight of each one, and figure out which one's optimal. There are some homework problems that do that. And then, so that's what we're doing, I guess. We're making a table. So here I've made a table, all possible Hamilton circuits from starting at A, and the cost of each one, and I find the cheapest one, $762. Oh, there's more of them. In fact, second group of 12. There's got to be 24 of these guys, right? I think so. So 741. Oh, there's a 676 guy. And so in so doing, we could find the optimal. Or we could go cheap. We could start from the home city, and we could go to the city that is cheapest to get to. And from there go to the next cheapest one, there to the next cheapest one until we get back home. And that would be instead of doing an exhaustive thing, we could just do that. That cost us $773, which is $97 more than going the other way. So maybe it would be better to pay somebody to find the right solution. But with fringe benefits, that would push up the cost. It wouldn't work very well. Now, if I had 10 cities, then my problem is I have all these paths, because all the cities go to every other city. Unless I go to Omaha, then I only have 3 airplanes out of here going 3 places. Then that's pretty bad. Now I've got a whole list of cities to go to, a whole list of prices. There are 9 factorial Hamilton circuits, so I have 362,000 possible populations. That could take 1,500 hours of work. No, I better find a cheap way to do that. I don't want to do that. Okay, so my cheap way would be to, if I start at A, go to the cheapest guy first. I go to C. Now I'm at C, I go to the cheapest guy next. But I've been at A already, so the cheapest guy after that is D. So I go to E. I go to E next. Now I'm at E, and the cheapest guy from E, given that I've been to the other 2 guys, is D. And now I'm at D, and the cheapest guy, given that the other is B, and now I'm at B, and the cheapest guy. And I would continue doing that process, only going to the cities that I'm supposed to go to. And if I do that, it would cost me $2,152, but that's a whole lot cheaper than finding every single possibility. Although I can imagine I could make a computer program to do it in seconds, if that. Okay, excellent. So that puts us at 6.4, which means we don't have to go any further than that, and we'll work another homework problem or two. So the last homework problem was 27. So we're going to do 29. Okay. 29. Okay, for the graph below, find the optimal tour. From where to where?
That's all the way around, right?
Okay, so it doesn't matter. So I can go A, B, C, D, or I can go A, C, B, D, or I can go A, D, B, C, or I can go A, D, C, B. Those are my only choices, right? Four of them. I think those are my only choices. All right, so now I add them up. A, B, 48 plus 32 plus 18. But what, am I doing a tour or am I doing
An optimal tour.
okay, so I'm only doing a tour, so I don't have to go back. All right, A, C to B to D. A to D to B to C. A to D to C to B. Okay, so those are all my possibilities. 10, 30, 40, 50, 98. 20, 40, 50, 80. This guy's 80. 30, 20, 40, 74. 30, 30, 62. That guy wins. And you already told me that guy won. So Scott told me that guy won already. If I would have paid attention, we would have been done with the problem already. All right, so problem B. I want the nearest neighbor tour starting with A. All right, so if I start with A, I got to go to the nearest guy, which is D. And once I get at D, the nearest neighbor would be C. And once I'm at C, we're going to go back to B and then to, but we don't have to go to A because it's a tour. Okay, it's not a circuit. Okay, nearest neighbor tour. Okay, so that's that guy. C. We want the nearest neighbor tour starting at C. So if I start at C, I go to D because he's cheapest, and then I go to B because he's cheapest, and then the only guy I'm not at yet is A. And it doesn't ask for anything other than that, so we're done.
You skip over C.
Huh?
C, you start with B, and then D, you start with C.
Oh, I left
Left one out.
shit. So I got B and I got D, but I don't have C.
Yep.
Well, you know it. C. Nearest neighbor tour starting with Bravo. Okay, I'm at Bravo. I'm going to go to D, and then I'm going to go to C, and then I'm going to go to A. All right. That better? All right. And that was 29. Looking at 35. 35. Darren is a sales rep whose territory has 6 cities, mileage shown below, and blah, 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 blah. His home city is Atlantic. His travel costs 75 cents per hour. Find the nearest neighbor tour with Atlantic as the starting city. What is the total cost of the tour? Find the nearest neighbor tour using Kansas City as the starting city. Write the tour as it would be traveled by Darren, who must start and end the trip in Atlanta. What is the total cost of the tour? Okay, I think I understand. It's almost written in English. 35. A. Okay, so we're going to start at Atlanta. And we're doing nearest neighbor. So if I start at Atlanta, the nearest neighbor is Columbus. So I go to Columbus. Once I'm in Columbus, the nearest neighbor from Columbus would be Kansas City. Okay, and once I'm in Kansas City, the nearest neighbor would be Tulsa. And once I'm in Tulsa, the nearest neighbor that I haven't been to yet would be Minneapolis. And once I'm in Minneapolis, the nearest neighbor would be, that I haven't been to, would be Peoria. Alright, so there's my tour. Now, no, we still have to get back to the beginning on a tour. I'm pretty sure. So we still have to end in Atlanta.
No, it's not Atlanta.
Yeah, we still have to end in Atlanta for the tour. It's not a path, it's a tour. So we may want to go back and revisit the other guys. Now we got to write down costs.
Oh, yeah, because the other one's a tour.
Yeah, they wanted tours and I only did paths. We'll just put whatever it is at the end. All right, we'll go back. We'll revisit that.
That wasn't bad.
So I wanted a
For
tour,
that one, yeah, I was gonna say that, screw that up, so.
29A. Find the indicated tour. So optimal
You got that A of the whole, the rest of the.
yeah.
Yeah.
I'm gonna have to add an A.
Yep.
A, and go, so D to A would be 22, and plus 22, C to A,
28.
28, and B to A, 48.
48, yeah.
Alright, so now I got 120, and I got 102, and I've got 100 and another 102, another 102, and then I've got 110. Okay, so I got two that are the same. Alright. And then I got to go back to A, and I got to go back to C, and I got to go back to B. Alright, just one of those things. Okay, so back to 35A. Atlanta to Columbus, 533. Columbus to Kansas City, 656. Kansas City to Tulsa, 248. Tulsa to Minneapolis, 695. Minneapolis to Peoria, 394. Peoria back to Atlanta, 1361. And so now I got to add all those guys up and multiply 0.75 to get my answer.
Yeah, he looked, gotcha.
So I've got 3887 times 0.75. So it looks like 2915.25. Maybe. If anybody agrees.
I'll agree to that.
Perfect answer. All right, now find the nearest neighbor tour starting using Kansas City as a start city. Write the tour as it would be traveled by Darren, who must stop and end in Atlantic. Okay, so we're going to in Atlanta. So we're going to try it again. Okay, so B. So we gotta go from Atlanta, and we gotta go to Kansas City first. That's our plan. So we go to Kansas City. Now we're in Kansas City. We would go to Tulsa next. Once we're in Tulsa, we would go to
No,
no.
you gotta Kansas City as a starting city.
Read it again.
No, but you have to start.
I have to start and end in Atlanta.
Then Kansas City.
So it's a tour starting at Kansas City, but starts and ends in Atlanta. Okay, you could have written the problem better. I agree. No accounting for how math majors write in English. And who says that what we're doing is really right? You know what I mean? All right, so anyway, I'm in Tulsa. And the nearest guy is Minneapolis.
So we'll just follow the last one.
And then from Minneapolis, I'm going to go to Peoria. And then Columbia. Then back to Atlanta. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, so that's what we're going to do. So that's my plan. Now we're going to add some numbers together. Atlanta to Kansas City. So 7, 9, 8. Kansas City 2, 4, 8. Tulsa, Minneapolis 6, 9, 5. Minneapolis to Peoria 3. I don't recall going to Peoria last time. Peoria,
Yeah.
we did? Okay. 1071. Go to Columbus. Columbus, Kansas City 5, 3, 3. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right. So, assuming that I did that right, then I'm going to multiply by 0.75, and I'm going to get an answer starting with a dollar sign.
Hopefully.
So that's my plan. 7, 9, 8, 2, 4, 8, 6, 9, 5, 3, 9, 4, 1, 0, 7, 1, 5, 3, 3 equals. I get 3739 times 0.75, 2804.25. I hope that's more than last time. No, it's not more than last time.
It's less.
How can it not be more than last time? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We're missing something. No.
No, because Peoria to Atlanta, that's the most, that's the longest.
Yeah. Yeah. Okay.
The one you got is
All right. So we're okay, but we. Now how can that be?
No.
Something's wrong. Oh, I see. Because we started in Atlanta last time and went to Columbus, that gave us a longer path than if we go Atlanta to Kansas City. Okay, I'll accept that. We could look in the back of the book, but that'd be way too much work.
I'll give them for
35. Okay, next guy is 37. Okay, the next guy says repetitive nearest neighbor algorithm. Do those words cross our lips so far?
nope.
Okay, so we obviously can't do that problem. If I had a pen, which I do right there, I would mark that we made it to there. Okay, so the next thing we're going to do is the quiz. Okay, so we'll come up here. So what do I need? What's my name? What's my password? I don't know. I wish it was. Unfortunately, I have to change my pen. Don't even have my longest. CO part. Okay, so we're there. We're here. We're on the Buena Vista website, which of course has a different password. And there's Angel. Has a different logon and a different password. Okay. Oh yeah, that's very good. And that's this semester. Tools, grade book, assignment. Well, this is week 4. No, this is week 5. Okay, week 5, quiz 1. Week 5. Worth 10 points. Okay. Control Alt